So we're going to be starting now. Let me know if my audio is difficult to understand or anything. But this is also, if you have any questions, just as a preface for this whole thing, feel free to either raise your hand or leave a question in the chat, or just unmute yourself and ask. Questions are wonderful. So this is day 2 of our 2539 Team Krypton Cougars programming workshop. I am Matthew Milunik. I'm the lead programmer on Team 2539, and I will be your host for today. So today, as you can kind of see from the name, we're going to be learning how to program tank drive. So welcome to day 2. Thank you for coming back. If you were at the first one, if you're new this time, that's perfectly fine. The previous session was posted on YouTube if you'd like to see that on our YouTube channel, Team 2539 Krypton Cougars. So for today, first we're going to review some of the Java fundamentals that we learned last time, because they're fundamental and they're fun, I promise. And then we're going to learn some new ones, specifically loops, since we didn't get to those last time. Then we're going to go over programming tank drive, which is pretty basic, basically the basic form of driving for robots and FRC. And it's a lot easier to program than Surf Drive. And then for our lab, we're also going to be programming tank drive. So as you can see, for our 2024 programming workshop timeline, we're on day 2 out of 6 doing tank drive. Next time we'll be aiming with Limelight, and the last time all we went over was Java, motors, sensors, and controllers. So for review, we have variables, right? Variables are containers for storing data values, for example, strings, integers, and doubles. And as an example of how you would create one of those, if we go into my Java view here, if we wanted to make, for example, a variable holding our age.
Sorry for interruption, Matthew.
Variable, then whatever we want to call it equals, and then whatever my age is. In my case, 17.
Hey, Matthew, can I ask a question? Are you sharing your screen?
We also have conditional statements, which will run based on a Boolean. So if the Boolean is, I guess a conditional statement is an evaluation that uses multiple values to determine a Boolean. And you would usually use it in conjunction with an if statement or an if-else statement, which executes a block of code based on the conditions. So an example of that, just reviewing from last time, the if, and then we could do, or actually, let's keep my age, and let's say if my age is greater than, using this greater than sign here, or equal to 16, then we can print out that I can drive. So system.out.println can drive, assuming I get my license, of course. And then else, if I'm not 16 or older, we can print out that I am not able to drive. So this, for example, is going to print out can drive if we try running it.
Are you sharing your screen?
Can drive because I'm over 17. So this conditional statement evaluates to true, and it runs this first block of code. If I was under 16, like I was 5 years old, it would run the second statement, as we can see here, hopefully, not able to drive. So our program worked correctly. So there's also methods, which are callable functions that can kind of do a certain section of code for you without you having to rewrite it. Using our example we're building on, if we wanted to say check if another person was able to drive, but we didn't want to rewrite this section here, we can make a method called is able to drive, right? Or check is able to drive. Like this, and then we can pass the age as a parameter. So the way you define a parameter is very similar to how you define a variable, You just don't include the setting part. So we could do int age here. And then we can copy this code, insert it here, and now we have a method that can do what we were doing previously. So now we could do check is able to drive for a 5-year-old, but without rewriting all that code from earlier, we can also check if a 15-year-old would be able to drive, if a 17-year-old would be able to drive, and if, say, a 40-year-old would be able to drive. And if we check all of those, what we should find is that the first two aren't able to drive, which makes sense, and the last two are able to drive. So that's how you use a method. Now, classes are kind of like blueprints for objects. They include fields, constructors, and methods. In our example, hello world is the class. These two are both methods. And we don't have any fields here. But for example, we could make a field called, per se, number of people able to drive. Something like this, public static int number able to drive. So this would be a field of the class. And perhaps every time we check if someone's able to drive and they can drive, we can increase that by 1. Like that. And now if at the end, we were to print out that number, we should see 2, hopefully, assuming the code works, which we see right there. So this would be an example of a field in a class. Any questions so far on this review? Okay, in that case, we will move on if no one has any questions. Let me get my laser pointer on. I like the laser pointer more than the mouse. So this is the example of an else if statement that we kind of went over with the example I gave. But if else statement, just a reminder, is like an if statement, but if you go to the else section, it does a second if statement, and then it goes to else. So this one kind of prints out just a statement about x, which depends on what x is. Here's an example of a method, again. And here's an example of a class that would be a little more common to a robotics use case, where we have our motors as fields, our drive subsystem as a constructor, which is basically a method you call using the keyword new to create the class. And then we have a method that just sets speed. When making a method, if it has this little bit that says return at the end, it means that it kind of turns into a value when you're using it, which we'll see later. So any questions about that? Okay, we'll move on. So for our new Java fundamentals for this session, we're going to be going over loops. So loops repeatedly execute a block of code as long as the specified condition is reached. Using loops can save time, reduce errors and redundancy, and increase readability. There are several types of loops in Java, specifically while loops, which loop as long as a certain condition is true, and for loops, which repeat a specific amount of times. So while loops, here's the syntax. You write while, and then in parentheses, a conditional statement, and then some code that you do while that conditional statement is true. So for example, in this lower thing, we define a variable called I. It's an integer, and it's set equal to 1. While I is less than or equal to 3, so in our case, like 1 would be less than or equal to 3, 3 less than or equal to 3, it will execute this code. But if I is not less than or equal to 3, like let's say it's 200, right? This code won't run, and the loop will end, and the code will kind of just keep going after the while loop. this code right here, what it's going to do is it's basically going to print out I and then increment it using this plus plus syntax. What the plus plus means is it means take I and add 1 to it. So this is pretty common syntax you're going to see in Java programming because very frequently we want to add 1 to a number. If you see minus minus, it means subtract 1 from the number. And the output of this program is 1, 2, 3, because we start with 1, which is less than or equal to 3. We print it out. We add 1. 2 is also less than or equal to 3, so we print it out, add 1. And then 3 is less than or equal to 3, so we print it out and add 1. However, since 4, which is what comes after 3, is not less than or equal to 3, it does not run the code block and it goes on to the next thing, which in this case is nothing. But if you had something after the while loop, it would do that. So if you can, open up either Programiz or some other thing you can use to run some Java code and try to create a while loop that runs until your age and prints your name each time. So what we want the output to look like is, if say you're 5 years old, 1, your name, 2, your name, 3, your name, 4, your name, 5, your name, and then that would be it. I'll try to get in the chat a link to Programiz in case you guys don't have that already. But yeah, I'll give you guys a few minutes to work on this problem, probably around 2-ish. But let me know if you have any questions. If you guys need to see the syntax for a loop, I'll put that back up on the screen real quick. So in the name of time, we're going to move on to the solution, which this is the example for Krypton Cougars. I think it's 1 year off, actually. But if we were to run this, it would print out Krypton Cougars 16 times. So for loops are another type of loop. Basically, they have a little tiny bit of code here that runs when they start. They have this little bit here called the condition, which is just another conditional statement. And then they have this little block here, which runs after every single iteration of the loop. So another way of viewing a, Another way of viewing a a for loop, is as a fancy way of writing a while loop. I know that this kind of can make it a little more clear how some things happen. So this example of a for loop down here, before it starts, it runs int I equals 1, and then it checks is I less than 5, and if it is, it runs this code block. And then after it runs the code block, it increments I. Then it checks is I less than 5. If it is, it runs the code block and increments I. And then it keeps doing that until I is not less than 5. So if you were to write that as a while loop, it would look a bit like int I equals 1, while I is less than 5, system.out.println I. And then at the end of that while loop, we're going to put an I++. So this here is equivalent code to this here. It's just often you'll see it written as a for loop because it's a lot more compact, and it makes it very clear that you're just kind of iterating on a number. Whereas while loops, you can do a lot more complicated things with. And also for loops give you a lot more certainty that they're going to end at some point. Whereas while loops, for example, if you messed up this definition, could go on forever. So, and if we run this, as we can see, this will output 1, 2, 3, 4, all the numbers less than 5. But also, if we were to write out the example given in the presentation right here, that should also print out the exact same thing, 1, 2, 3, 4. So for this one, it's the same project. You just need to rewrite your while loop as a for loop. And I think you guys probably have the project memorized by now since you did it last time. So I'll actually just go back to the for loop syntax so you can see it again. And I'll give you guys about 2.5 minutes to complete this one as well. So again, in the name of time, we're going to be moving on. Hopefully you got this one. If you didn't, it's okay. There is a learning curve to this stuff, so feel free to work on it more on your own time. In the last presentation we had, we linked some learning resources, specifically Code Academy. We highly suggest you look at that if you're uncomfortable with this. But we're going to be showing the solution now. So this is our solution, at least. Basically, we start with age equals 0, and we run up until the age is just under 16. So in this case, it would be 15. And we add I, we increment I every time we print out the Krypton Cougars name. So for a loop like this, usually in programming, we will start with 0, and we will run until the age is less than 16. Alternatively, you could start at 1 and run until the age is less than or equal to 16. So just make sure you do either 1 and less than or equal to, or 0 and less than. If you mix and match those, you'll either end up printing Krypton Cougars one too few times or one too many times. So that's it for the Java section, or the, I guess, Java fundamentals section of our presentation today. And we're going to be moving on to tank drive now. So without further ado, I guess, let's get started. This is swerve drive, right? In FRC, swerve drive is pretty common at this point. Among rookie teams and starting teams, it's less common, but it has become, in the recent years, a very common method of, I guess, driving your drivetrain around the field. We're not going to be focusing on that today. We will focus on that at a later day, day 6. Today, we're going to be focusing on tank drive. So one of the benefits of swerve drive is that your robot can kind of move side to side without turning. Tank drive does need to turn because, as you can see, it only has these wheels on the left and these wheels on the right. It drives like a tank, kind of, hence the name, but also a lot like a car. So cars, they can't go sideways. They need to turn to go sideways. So that's kind of how tank drive tends to operate. But this also means it's pretty simple to program as far as things go, because all you need to worry about is how fast your left side is going and how fast your right side is going. So as far as control methods for tank go, this one is called differential drive. It's pretty simple. Basically, you have one axis of your controller, in this example of the y-axis on our left joystick, controlling the speed of the wheels on the left of your controller, and the y-axis on the right side of your controller just controlling the speed of the wheels on the right side of your robot. So it's very simple to program. You're pretty much just taking the output of one axis and plugging it straight into the motor output of the wheels. If you want to drive straight, you just push both of them forward. If you want to drive backwards, you just push both of them backwards. And if you want to turn, you push them in differing directions. Now, arcade or curve drive is basically a differing form of control where instead of controlling each side independently, you instead have one axis, right here, this vertical axis, which controls how fast the robot is going, kind of, or a forward component, you could say. One joystick controls forward, back, and your other axis, right here, which is left to right, controls how much your robot is turning. So you can kind of think of this one, if we're going with a car metaphor, as the gas pedal, and this kind of as the steering wheel. In arcade drive, it's a bit different to that, because if you turn this to the left, even if you don't have any gas going, right, your robot's still going to turn. In curve drive, the difference is you need to be moving to turn. So arcade drive, your left to right, controls the speed at which you're turning, whereas curve drive controls the radius of your turn. Today, we're only going to be going over how to program arcade drive. because it's a bit simpler and it doesn't come with as many nuances. So command-based programming is kind of the paradigm that we're going to be using to program this in. And generally, it's the paradigm that most FRC teams using Java end up using. And it's also the one we recommend. So basically, in command-based programming, you have two main new concepts you kind of have to learn about. There's this idea of subsystems, and there's this idea of commands. So subsystems you can think of as a combination of motors, sensors, actuators, or possibly cameras that function together as kind of a collective mechanism on your robot to do a specific thing. And usually they're going to be working together. So, for example, we have the drivetrain. That could be all the wheels on the bottom of your robot. For tank drive, that would be like the motors powering them. If you had sensors on those wheels for odometry, those would also be part of the drivetrain. You could have a gripper, for example, to hold a piece. Maybe the motors that actuate that gripper, or the pneumatics that close that gripper, and the sensors that detect if there's a piece in the gripper would all be part of that subsystem. And a ball shooter, for example, could just be the motors that are spinning the flywheels to shoot a ball. So a subsystem is a type of class that has as fields all the classes for all the motors, sensors, and anything else in that subsystem inside of it. And usually it'll have methods on it to set specific things about those motors or actuators or sensors, methods to read things from those motors. And also, one thing that, at least in the way we program our robots, it's going to have is a lot of methods that return commands. So commands in that sense are basically processes that have a start, a during, we'll call it, and an end that a subsystem can take part in. So, for example, move to scoring position, right, is a process that the drivetrain can do. Stow wrist could be a process that the gripper could do. Deploy minibot could be a process that the minibot launcher does, for example. So all of these are processes. They're not collections of motors. They're not collections of sensors. They're actual things your robot can do. And we're going to see that there's many ways you can combine commands together to make bigger commands. And there's a few ways to define commands, which we're going to go over. So subsystem-wise, if you look in WPILib, and I would recommend that if you downloaded the off-season training project last time, you open it up in VS Code now. I'll give you a little time to do that. I'll be posting the link to the off-season to the off-season training GitHub repo in case you would like to use it real quick. So just give me a second for that.
Yeah, you have to watch the WPI version.
So there's the link to the GitHub repository that we're going to be working off of primarily. But yeah. So here we see one second actually. we have some people working through some issues right now here, so I'm going to give them a minute. So hopefully you guys were able to find your way into VS Code. I have VS Code open here. This is actually on the final code that we should have by the end of the lab today. But as you can see here, I have my source/main, and then inside Java, we have subsystems. And I have a few subsystems here. You should probably only have one, probably named drive subsystem. And this basically has a bunch of motors in it, a bunch of methods that return commands that we can use to control the motors, and some methods that we can use to directly set drive speeds. So when we want to create tank drive, the first thing we're going to do is basically establish the motors. Last time we went over creating motors, but basically you need to define the class. In this case, we're using CanSpark max motors. So this is the class. And you need to use a constructor similar to this. So this is the constructor for the CanSpark max motor. In the GitHub project, if you check out the week 2 branch using, I'll make a little note, but using git checkout week 2, that has all the answers for this week, and it also gives examples of how to program tank drive using Talon FX motors and Talon SRX motors, in case you are or your team is using those. So, but generally, structure-wise, you're going to create your motor or define your motors up here. You're going to set them here, basically using the ports that the motor is running off of, and the type of motor, whether it's brushless or not brushless, if you're using CanSpark Maxes. Then you're going to usually set one of the motors to follow another one of the motors. So here we set the left follower motor to follow the left leader motor, or the right follower motor to follow the right leader motor. You would do this if you have 2 motors on the same side of your robot. So in our example, we have our robot here, and we in fact have 2 motors on this side and 2 motors on the other side. One's here, and then on the other side we have 1 here and 1 here. So that's why we're using 4. I know some teams might use just 1 on each side. Some teams might use 3 or maybe even more on each side. In that case, create as many motors as you need, but usually it's 4. So in that case, really we want to be able to set the speed of an entire side by only setting 1 motor speed. One way to do this is by using a method call, where inside that method, you take as an argument 1 speed, and then you set all your motors. But the way that is recommended is to use this .follow command. If you're using CanSpark Maxes, this is how you do it. If you're using the other motors, that example is given in the answer key, I guess, for the lab. And also, there's a chance you're going to need to invert your motors. Basically, sometimes when you just put the motor on the robot and wire it up, if you just tell it to go 1, that direction it ends up going might actually be backwards, not forwards. And also, depending on how the motors are mounted, you might need to invert your follower motor so that when you tell your follower and your leader to both go forwards, they spin in the same direction that works together, as opposed to just like pushing against each other and not getting anywhere. So usually this is easiest to find out by just like flipping them until it works. Or if you have a design team that really knows what they're doing, they can tell you if they should be inverted or not. So this is an example of how you would create a drive command. Basically, command-wise, it's just a method. It returns a command based on this command type here. And it takes two things called double suppliers, which for now, I'll just show you a little syntax you can use to make them. But think of these as objects that you can call a method on to get a double. So instead of just passing a variable or a single number for what left axis should be, and for the entire duration of the command, it's staying the same, you can pass this, and during your command, it will change. This little run thing is a method call that takes an arrow function. So that's kind of what this arrow thing is here. For now, you can just think of it as a syntax you kind of need to use in this case. But what it does is it runs this block of code in here every 0.02 seconds or every 20 milliseconds while the command's running. And this method here, at least, is defined to run the left side of the robot at this speed and the right side of the robot at this speed. So an example of drive control schemes for driving the robot, this would be tank drive or differential drive. The left side of the robot just gets driven at the left speed, or in this case, set to the voltage of the left speed times 12. You could also just use set percent or just set plainly, and you don't have to worry about the times 12. And the right side gets set to the right speed. Drive arcade is a bit different. What this does is it takes one thing, which is speed in the x direction, so forwards, and it takes a z rotation, which is pretty much the rate at which we're supposed to be rotating. Now, the way this works is left speed is equal to our x speed minus our z rotation, whereas the right speed is equal to our x speed plus the z rotation. So if z rotation is 0, the drivetrain should just go forwards at the same speed on both sides as x speed. And if x speed is 0, our drivetrain is basically going to go backwards on one side, but forwards on the other side at z rotation speed. So it's going to turn. And now if neither of them are 0, it's going to do a combination of those where it drives forwards, but at the same time is turning. So that allows you, instead of individually controlling each side, you can have a drive and a turn, which for a lot of people is more intuitive. Now, robot container, we kind of went over this in the last presentation during the lab section, but this is usually where you're going to define any controllers you have. It's where you're going to kind of store the subsystems you have and where you're going to create them. And it's also where you're going to bind your commands that you make from the subsystems to your controller down here. So for example, using the previous examples, this is how you would set a default command to drive. You would have our joysticks up here, right? Left joystick, right joystick. We would have a method on them that we use to get the left axis, get the right axis. This syntax here, basically, this is a keyword that means the current class, kind of the class we're in. Get left axis is just the name of a method. These double colons basically mean call this dot get left axis parentheses, but put it behind the nifty arrow syntax. When we give the example of this, we won't write it using this double colon because it makes it a little more difficult to understand. Basically, this returns a command right here, this section, and then this sets the drive subsystem to use it as the default command. So anytime no other command is running, it's going to be running that command. Since we don't have any other commands that would run, that pretty much means it's always going to be running that. So axes and deadband. when you have a joystick, which I think I have one over here, so okay. My wonderful mentor is getting it for me. But if you have a joystick like this, for example, sometimes when you're not even touching it, it'll still register a tiny bit of kind of being pushed. So for example, right now, I'm not touching it, but maybe it would register 0.01, right? In that case, you don't really want your robot to be moving. You want it to be stopped. So deadband, what that refers to is how large your joystick input needs to be for it to not be 0. In this case, we're manually making sure that if the input is less than 0.05, we just return 0. Otherwise, we return the value. And we're applying that on both the left and right axis. So time for the lab. Basically, for this lab, we're going to be creating a drive subsystem that has tank drive using 4 Neo motors and 2 joysticks. We're going to be implementing arcade drive on it. We're going to be using a button to switch between driving modes, to set one as the default mode and one as something that you can use a button to press as a toggle to switch to. And we're going to have a button that basically turns the robot around 180 degrees real quick. Here's a QR code to go to the WPI lib docs if you need those. Here's a QR code for this presentation if you need that, which I hope works. If you guys have any questions about any of the stuff we went over before we jump into the lab, now would be a good time to ask. So if anyone has any questions. So apparently the QR code for the presentation does not work, so I'll be posting the link to it right now. So that link is in the chat now in case you need it. So in that case, we're going to be moving on to the lab section of this presentation. So if you have an actual robot, now would probably be a good time to turn it on. And now is also a good time to open up WPI lib. So we can just be starting off where we left off last time, with our single motor and our drive subsystem. Looks like I don't even have my single motor. I must be on a different branch than I was previously. Okay, here we go. Correct version of the code. But starting off with our single motor, right? So we have a drive subsystem, right? We have at least one motor. Basically, we need to repeat this 4 times. So you can copy and paste that first motor if you have it. But just as a recap, you have CANSPARK max, the name of the motor, an equals sign, and then new CANSPARK max, the port the motor is on, and then the type of the motor, in our case, brushless. So for us, we have 4 motor controllers, right? 1, 2, 3, and 4. And each of them go to a motor. This one goes here, 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 and this one goes here. So our front right motor is going to be 1, our back right is going to be 2, our back left is going to be 3, and our front left is going to be 4. For our robot in specific, your robot's probably going to be a little different. So now is a good time to ask your mentor about any of those ports if they're different. So here I'm just defining motor front left as the CANSPARK max on port 1. And I'm just going to do that for the rest of the motors. Okay, so as you can see here, I've created those 4 motors, all CANSPARK maxes, front left, back right, front right, all with different motor IDs. We still have this proximity sensor in it. If you want, you could delete it. We're not actually going to be using it for this tank drive example. I'm just going to leave it in for now. We can leave this in too, but it's not really necessary anymore. Down here, we have our run motor command. We don't really have a single motor anymore to run that we're really going to want to run by itself. And we also don't really have a single motor we're going to want to set speed by itself. So we're going to delete these 2, or you can just comment them out. A tip to quickly comment out a lot of stuff, which is commenting, in case you don't know, is putting these 2 slashes in front of your line. It pretty much tells Java not to pay attention to anything on the line, to pretty much just skip and ignore it. In VS Code, a shortcut you can do to comment out or uncomment a lot of code very quickly is pressing Control on your keyboard and then pressing slash. Or if you're on a Mac, pressing Command and slash. Just a reminder, if you're getting issues where, say, SparkMax isn't appearing, make sure you have this at the top, and also make sure that you have your vendor libraries properly imported.
Oh, can you put the link for Spark?
Yes. So if you don't have the vendor library for SparkMaxes, because I know some of you guys here weren't at the last one, and we have some people here who didn't quite get the SparkMax library installed last time, I'll just quickly go over how to install that. So what you're going to want to do is you're going to want to open up, say, Google, right? You're going to want to open up Google and look up WPILib third-party libraries. And then click on the first link. Then you're going to want to scroll all the way down until you get to this section that says libraries. And you're kind of going to want to scroll until you find the exact one you need. We are going to need Rev Robotics RevLib, which is this link right here. So you're going to want to copy that link. I'll post it in the chat in case you need it. And if you're using a Talon FX or a Talon SRX motor, you're going to want to use either Phoenix 6 or Phoenix 5. I would totally recommend installing both. But if you're going to use any CTRE products, that is. So using that link, you're going to want to press on our little W up in the top corner here, and then type vendor, and manage vendor libraries should come up as your top result. Click on that, click install new libraries offline once you get there. Also, let me know if I'm going too fast. I can slow down a bit. But once you get to this window, right, you're going to want to press install new libraries and then paste in that link. And then press enter, and it should install for you. If you already have it installed, it'll give you this little notification down here saying it's already installed. I already have it installed. If not, it should basically install the library and try to build your code. It might not work if your code is in a messed up state. Like, for example, mine right now is in a messed up state. I have an error. Your build won't succeed, but you should have the library imported now. So to get to this thing where you get the install, you need to go up to the top right corner. I just got a question about this. The W in the top right corner, click on it, type vendor. So your bar could look a little like that. And then you want to click manage vendor libraries. Then you want to choose install new libraries online right there. Then you can paste in the link, press enter, and it should install for you. So hopefully you guys all have your vendor library installed now. You guys all good? Okay. So hopefully now can Spark Max is showing up. If you just type can Spark, it should be one of the options, and then you do M, probably going to be the first one. Press tab, and that will automatically import it up top here. If you don't have it imported in your file, you technically won't be able to use it. I always recommend using tab to do the import because it just automatically gets the right path for you and you don't really have to think about it. If we were to delete this, for example, I would get all sorts of errors about can't find CanSpark Max. So. I'll just give you guys a few more seconds to make sure you have all this kind of looking the same. But okay. So moving on, we're going to need a few configurations done to these motors, right? So specifically, we're going to need to set followers and we're going to need to be able to set inversions. So first, we're going to set followers. In our robot, at least, we're going to want the back motors to do what the front motors do. So that way we set the speed of the front motor. So we're going to do motor back left dot follow. And with CanSpark Maxes, this is very easy. You just put the motor that you want it to follow as the parameter. And this is usually good enough. But if you need to invert the motor so it kind of goes the opposite direction of that first motor, depending on your gearbox or the mounting, you might need to do this. You can do true if you need it inverted, or in our case, we're just going to assume false for now and change that later if we need to. Then we're just going to want to do the exact same thing, but with the right side of our motors. So now we've set the followers, but we still might need to invert our front motors. So we're going to do set invert, just leaving a comment there. That way people looking over our code can understand it. And then we're going to do motor front left, because we're setting the inversion on the front motors. Set inverted, and we're just going to default to false for now. But very simple on Spark Maxes to set inversion. And we're going to do the same thing on the right. If anyone has any questions, you can leave them in the chat. Now's a great time to ask. We're going to continue then. If any questions pop up, feel free to ask. So to be able to easily control these motors, what we're going to want to do is create a method that allows us to set the left speeds and the right speeds at the same time with just one method call. So we're going to call this one set speeds. And we're going to take two parameters, a double or kind of a decimal value, right? That can be anything in between 0 and 1, or in this case, anything between -1 and 1. And we're going to call it left speeds. And then we're also going to make one for the right side. And all we're going to do in here is we're going to use our knowledge from last time as for how to set the speed of a motor, motor.setSpeed. And we're just going to do it with the left and the right side. So motor front left dot set and we're going to do left speed. Ugh. And then we're going to do the same thing on the right side. So now we have a fully functioning method that should allow us to, with one method call, set the speeds of all the motors in our drivetrain and kind of allow our drivetrain to drive. But to be able to bind it to a button easily, we're still going to need to turn that into a command. So to create that command, we're going to make a method that returns a command. And the way you do that is you use the command word, the command type, as the return type right here. Up here we used void because it doesn't return anything, and void is the special keyword for that. But here we're using command because we want to return a command. So public command, and we're going to call this one tank drive. Now we're going to take in a double supplier this time. So or actually, probably the best way to do this is not to put a double supplier here. We're going to create the command outside of the class for now, just for simplicity. But if you go into robot container, right now we have our default command being this. Basically, it runs and it sets our motor speed to our main joystick.x. What we want to instead do is run mdrive subsystem.set speeds. And we're going to want to make the things that we put in here equal to our joystick axes. Right now, we only have one joystick, so we're going to create a second one. That is not how you spell joystick. Right joystick. And then new joystick 1. So this one we're going to rename to left joystick. And the easiest way to do that is to, I guess, just simply change the name. But if you have it referenced in a lot of other spots, like right here, we have it referenced here. So if we change the name here, we'd get an error here. In VS Code, at least, you can right click on it and you'll get this big drop-down menu. You can choose rename symbol, or you can press F2. And then you can change the name of it. We're going to change it to left joystick. And when you press enter, it'll change all the occurrences of it, as long as you don't have errors in your code. I have an error in my code right now, so it's not letting me do that. It's very mean to me. So now I have no errors in my code. But if we rename the symbol, or no syntax errors at least, to left joystick, it'll rename both of them. So that's a useful trick to do if you're changing your code and you don't want to go through all 20 times you wrote out your variable. But down here, we're going to go back to this. And we have our run command constructor, right? So this creates a command that uses the drive subsystem, and it runs this repeatedly. Set speeds. So right now, if we were to run this command or deploy this program to our robot, all it would do is it would set the wheels to not move at all, which isn't really what we want. We need to get the speed from our left joystick and our right joystick because we're just doing simple differential tank drive right now. So to do that, we can do left joystick dot get x, and then right joystick dot get x. It's basically every 20 milliseconds, it calls this method, which checks what our left joystick is set to and checks what our right joystick is set to, and then sets the speeds of our drivetrain to those. So I'll leave this up on the screen for a little bit, but I'm going to deploy to our in-house tank bot right here. That way we can test out this code. If you have any questions, now's a good time to ask because it may take a while to deploy this. If you're at the same stage at home and you're also deploying, make sure in your settings.gradle, I think, maybe not settings.gradle. There is one spot where you need to change your team number. If you pulled the code from our GitHub, it'll have our team number. You'll need to change it to yours. A good way to do that is just searching your team number here. It's in WPI-lib preferences. So right here in this .wpilib folder, you need to change your team number. So my code successfully deployed, which means that now we'll be able to test it out. So on our driver station over here, we are actively connected to our robot. And so if I go over here, what I'm going to do is enable basically. And that's going to make our light start blinking. That blinking light means your robot's enabled. If your robot's enabled, it can basically do anything. Press enter to make it not blinking. If it's solid, your robot should be safe-ish to be around. Safer. But we're going to enable. And so right now, robot not doing anything, wheels not doing anything. If we try using one of these joysticks, maybe you can't quite see these joysticks. So yes, if you hear a bunch of clicking when doing this, either your gearboxes aren't set up right, or more likely, you need to invert the follower motor, where we did so earlier in the code. Specifically, here, you'd need to invert one of your motors. We're getting no clicking. Both of our motors are kind of just working. We didn't implement any deadband. You can see here, the motors are still moving, even though our joystick is like basically 0. That's why you'd want to implement deadband. On the left side here, we also have no issues. So it appears that we set up our followers correctly, at least.
Forward, relative forward.
One thing we did incorrectly, at least, is for these joysticks, we got the wrong axis. So we did side to side as our axis instead of front to back. So to figure out if we need to invert our values, we need to change that. Depending on your joysticks, front to back could be the x-axis or it could be the y-axis. So as you can see, I changed those to the y-axis. And I'm going to deploy again. If you guys have any questions, again, always feel free to ask. Hopefully the second time it deploys a little faster. Usually if you don't make very big code changes, your deploy will be slightly faster than if you make a lot of big code changes. So that time only took 14 seconds. So if we retest this, if I enable, right? If I go forwards here, my motor goes forwards. And if I go forward here, it appears to go the opposite direction. So what that means is that one of my sides needs to be inverted. Specifically, my left side needs to be inverted. So if we pop back into our drive subsystem, motor front left, set inverted, true. So then if we deploy this, again, you might have to deploy a few times for this. If we enable, our left side goes the right way now, and our right side does too. So if we were to put this robot on the floor, which we can do, it should be able to drive around now. One second. So we now have our very professional camera setup. But if we enable and I start driving, it is in fact able to drive around using the joysticks. We probably want to implement some simple deadband, that way we don't get the slight drifting while I'm not pressing the controllers that we're experiencing. But for the most part, this is functional as a swerve, not a swerve drive, as a tank drive. And I'm disabling there at the end, just to make absolute certain that the robot is off. Because if I had enabled, right, I could bump this, robot would go flying. That could be dangerous. So we're going to implement some very simple deadband right here. The first step we're going to do to make that happen is we're going to wrap this section here in curly braces. If you wrap it in curly braces, you need to add a semicolon. This is basically just, again, kind of a way of letting Java know that, hey, I don't want to run this code right now. I want to pass it to this method. That way it can run it later. So to add deadband, we're going to kind of extract that and put it here. Well, easiest way to add deadband is probably just to add a method. We're going to call it deadband public static double deadband. And then we're going to have our initial value and double tolerance. So if our value is less than the tolerance and it's greater than the negative tolerance, right? Because if we have our tolerance set at 0.05, right, we're going to want 0.01 to trigger it, but we wouldn't want -1 to trigger it. So it needs to be in between 0.05 and -0.05. And this here, this conditional statement, makes sure that it is below 0.05 and above -0.05. If it is inside that tolerance, we just want to return 0. we can use our else statement here. We want to return our original value. So I'll just leave this function up on the screen for a little bit. Something else you could do using math, java.lang.math, is you can find the absolute value of something. This is unnecessary. I'm just showing this as an example. But instead of checking if it's less than the tolerance and greater than the negative tolerance, you could just check if the absolute value is less than the tolerance. So this right here is an equivalent way of writing this. But I'll just leave this as this for you guys. Any questions so far? Once you have that deadband method completed, all you want to do is kind of call it on our joystick values with a tolerance of 0.05 is probably good enough. I'm just going to leave that on screen as I deploy this. But hopefully what this should allow us to do is have a nice tank drive without the jittering that we were getting last time, or the, I guess, the joystick drift, the Joy-Con drift. So I need to plug into the robot, unfortunately. So with our code now properly deployed, let me get out of the way before this thing like attacks me. It appears to still be moving slightly. I'm going to check our joysticks to see if we have a lot of drift. We in fact do. This one's actually at negative 0.06. So I'm going to increase our deadband to 0.1. But as you see, if I just slightly tap this one back, which is the mischievous one that's causing our deadband issue, the robot's completely still. We're not having that drifting we were having earlier. So I'll increase that to 0.1. And we'll deploy that robot code. So now if we enable our robot, as you can see, it does not move at all unless we touch our joysticks. So it's functioning. Now, one thing right there that you probably noticed is when I let go of the joysticks, the robot kind of drifted for a while. That means that our robot is in coast mode for braking. We might want, or I guess for stopped mode, it's in coast mode as opposed to brake mode. That is a setting on the motors. So we could do motor back right set brake. I can't quite remember exactly what it's called. I know on Talon FXs, it's called brake mode. Set idle mode. And then idle mode dot. Right now it's set to K coast. We could set it to K brake if we want. Usually, K brake is I would recommend for drivetrains because then if you let go of your controllers, your robot stops instead of coasting. Also, if someone tries to push you while you're stopped, you won't move as much. So here I'm just setting both of those to brake mode. The followers should actually, these should be the front motors. Sorry. The followers should basically just do what the front two motors do, in this case at least. And what that's going to have the impact of is our robot's not going to coast as far. And it also should make turning by just using one of the controllers a bit easier. Does anyone have any questions or a section of the code they want to look at a little more before we move on to Arcade Drive? So we're going to move on to Tank Drive. The way we're going to implement that today, not Tank Drive, Arcade Drive. Already did Tank Drive, or differential Tank Drive. We're going to do Arcade Tank Drive now. We're just going to make another method. It'll be pretty simple. Basically, public void set arcade speeds. And for Arcade Drive, we have a forward component and we have a turning component. So we're going to call this one forward speed and this one turn speed. Now we're going to have, just for clarity, I'm going to make a left speed variable, right? And we are going to set this to be equal to the forward speed plus the turn speed. And we're just going to leave it as that. Now, we're also going to have right speed, and that's going to be the forward speed minus the turn speed. So what this is going to allow us to do is the classic arcade style drive where one controls whether you're moving forwards or backwards, the other one controls turning, and if you use both of them together, it pretty much just adds those results together, and you drive forwards while turning. Now to actually use these, we already have a method, set speeds, so we're just going to call that. And that is our arcade speed method complete. So I'll just leave this up here for a second for you guys. But pretty much in a robot container, what we're going to do when we get there is we're literally just going to replace set speeds with set arcade speeds. And also, one other thing in addition to that we're going to do, since in Tank Drive, you control by going forwards and backwards on both sides, But in arcade drive, you usually control going forwards and backwards on one, but left and right on the other. We're going to make a new joystick axis that allows us to access that left and right. But we're going to keep the current axis we have. We're going to have it stick around because we're going to need it for the third lab exercise. So hopefully you guys have that down by now. If you don't, I will go back to it later. But in robot container, right, we have this default command. All we're going to want to do is change this from set speeds to set arcade speeds. Real simple transition there. You just add arcade. Hopefully you got that. Up here, we have left joystick.get y-axis, right joystick.get y-axis. We want to change this to an x.get x-axis. So 2 pretty simple changes. And hopefully now the robot should drive in arcade drive. One thing that you may find when running in arcade drive or tank drive is that when you move your joystick left and right, your robot doesn't turn the way you want it to. It turns the opposite direction. The easiest way to fix that for joysticks usually is just adding a negative. USB-B. Okay, and now we're just going to deploy our code. You guys should be able to do this over, well, I guess you wouldn't be able to do it over Wi-Fi right now because you're in a Google Meet. But normally you can do this by connecting to the Wi-Fi signal of the robot. For example, usually it would show up, but it'll have your team number in it and then the name of the radio.
LEDs on your so you only break mode on the leaders.
Well, I think there's a stuff.
You see that?
Okay, so once we get a visual of this, I guess. Sorry, just 1 second. As we get this camera angle corrected. So here's our robot again. We're going to enable. And as you can see, me just using one joystick moves it forwards, backwards. Using this one turns it, which is exactly what we want. That's what he said. And then if we use them both at the same time, it can drive while turning. So that's how you make arcade drive.
Have you explained the controller difference?
Controller difference?
When you use a controller versus joysticks?
Oh, so if you're using a controller like this, usually it's going to be an Xbox controller. If it's an Xbox controller, there's a class for that. You would just do Xbox controller. If it's something else, you're going to have to use a custom HID. So I kind of forgot exactly what class it is, but there is a page on WP Island for that I'll post in the chat. Most people, though, are going to be using either joysticks or a controller. So for now, we're going to move on to the next task, which is using a button to switch between those driving modes. So basically, the easiest way to do this is to set one of them as default and make the button toggle the other command on or off. So here's where we're binding our commands. And let's say that arcade drive is our default for now. What is the easiest thing to do is basically copy this down here and then save. So now you kind of have a second copy of the command here. Change this one back to the original tank drive. So basically, instead of set arcade speeds, just make it set speeds, and then get Y, get Y. So now we have up here an arcade drive command, and down here, a tank drive command. And to make this a little more clear, we can extract them out into command variables. So we can do arcade drive, and then we can make this one tank drive. And also, when you're writing the type out command, you can use tab. That'll auto import it at the top if it's not already imported here. So down here at the bottom, we still want arcade drive to be our default command. So we can do m drive subsystem. And if you're wondering what this m means, WPILib, something they recommend is using a little m and then an underscore in front of your variable names if they are a field. So these would be fields, for example. This is a field. They recommend using an underscore m. You don't really have to. It's just a recommendation. I semi-follow it. But drive subsystem dot set default command. And then we're just going to set that to arcade drive. Now, we still have our button from last time, our main button. If you don't have that yet, this is the code you would use to create it. Basically, trigger is just something that can kind of be true or false, and it has a lot of built-in methods to allow you to do stuff on that. Main button, just the name, and then we're using the new joystick button constructor. It just takes a joystick as its first thing and a button number as its second thing. And something to remember from last time, button numbers, unlike almost everything else, starts from 1. So in programming, most things start from 0. The button numbers start from 1 because that's how the USB input device specification is defined. It's just weird like that. So down here, we're going to take our main button. And last time we used while true. We're not going to use that this time. Instead, we're going to use toggle on true. So what toggle on true does is the command that's passed to it, when you press the button the first time, it starts the command, and then you press the button another time, it ends the command. And it just does that on repeat. So it's like a toggle switch. So for our toggle on true, we're going to want to run our tank drive command. So what this should allow us to do is basically drive around an arcade drive all we want, and then say for some reason we want to switch to tank drive. We can pull our trigger, and then we'll be in tank drive, and then we can pull our trigger again, and we'll go back to arcade drive. So I'm going to drive the robot over here real quick and deploy that. And now that we've successfully deployed, we're going to unplug so I don't tear a cord. And we're going to enable. We should still be in arcade side, which is correct. One thing turning and the other one driving. But then if we pull our trigger, other trigger, we switch to tank drive. So now we're in tank drive. We can do all the tank driving we want, and then switch back to arcade drive with the pull of this trigger. And we're in arcade drive again. So there's probably various reasons you want to switch your driving.
Mess with your driver.
You could mess with your driver. That's a fun thing. But that's how you toggle driving. So for our final thing, this is something that might make a little more sense to put on a button, is a quick turn. So say you want to be able to turn around 180 degrees really fast, right? If you just try to manually do that as a driver, you're probably going to either overshoot or undershoot by a significant amount. Or in order to not overshoot or undershoot, you might try slowing down and basically doing it slower than would be optimal. What you can do with a button is you can have the robot turn at a certain speed, maybe a very high speed, for a very short amount of time, but that very short amount of time can be very consistent. So you can get that 90 or 180 degree turn down pretty well. So what we're going to do for that is we're going to use our other trigger. So we're just going to create a new button, trigger, and let's call this quick turn button equals new joystick, and then right joystick, for us at least, button 1. And this is going to get our right trigger, or the right trigger button, specifically this one. Now let's make a quick turn command. So to do that, we're just going to make a variable called command quick turn equals, and then similar to above, we can in fact just copy this one for now. So right now it's identical. What we want to do is, instead of getting input from the joysticks, we literally just want to drive the left side forward at full speed and the right side backwards at full speed. So we can replace those with, instead of method calls using the deadband, just plain values. This is going to very quickly turn the robot at maximum speed, pretty much. The issue with this command is that it's going to run as long as we have the button held down right now. We need it to end after a certain amount of time. And right now, it's just going to keep going. So to make it end, we can use a method of a command, dot timeout, with timeout. So a timeout of 0 seconds would end the command instantly. A timeout of 1 second, basically from the time the command starts, it will kind of start a 1 second timer in the background. And once that's over, the command just stops. And in our case, our subsystem would go back to its default command. Since we're turning at full speed, just as a guess, I'm going to say maybe 0.2 seconds for how long this should be. That's just an estimate. If you wanted to make it turn around 180 degrees solely using time, you'd probably need to test a little bit to see what works best for you and for your robot, because different robots will travel at different speeds. Now, to run this, we can do quick turn button dot, and then there's kind of two options for this that I could see making sense. You could use on true, which previously we used while true, right? What while true does is, while your button is held down, it runs the command, and as soon as you let go, it stops the command. On true, as soon as your button is pressed down, it starts running the command, but it will just run the command until it ends. If you let go of your button, it doesn't care. Our command here times out after 0.2 seconds. So this is a case where it might make sense to use on true, because then if you hold down the button for less than 0.1 seconds, you'll still complete the full turn. I personally would use while true here, because in my mind, if the driver wants a full 180-degree turn, they're going to hold down the button for longer than 0.2 seconds. If they like tap the button accidentally and realize they don't want it halfway through, I would prefer to have the robot stop doing that command. So usually while true is the better option than on true, but it's good to know that both of them exist. While true is basically slightly safer because you can always stop the command. So we're going to do while true, quick turn. Also, in case you've been wondering, there also exists while false, which basically just does exactly what it sounds like. If the button's let go, it will run the command. So it's basically the opposite of while true. On false is the opposite of on true. Toggle on false is the opposite of toggle on true. So there's cases where you would use those. But right now, this is looking pretty complete. So we're going to drive the robot over here and then deploy our code again. So hopefully this is one last deploy for our session tonight.
Feels like a spot where if they're watching on YouTube, they should smash that.
Okay, yeah, if you're watching on YouTube, you should smash the like button now so that this deploy works. And it did. I hope you smashed the like button. We're going to give it a second before we test this. But, we have a robot crossing, it appears. So if we enable, right, we still have our arcade drive. Drive out there. Now, if we hold this button, it turns about that far. So clearly that's not the 180 degrees we wanted, but it is still turning and stopping. So to me, it appears that to get it to turn 180 degrees, I need to press it down 1, 2, 3, 4, 5, 6, 7 times. So I'm going to estimate that I'm going to need 1.4 seconds for it to turn around 180 degrees. So if I change that to 1.4 seconds and drive the robot over here to deploy my code. Also, like, I know I said to like the video earlier if you're watching on YouTube, which like none of you guys actually watching right now, unless you're on YouTube, you should also subscribe because, you know, our channel is cool. We'll like post more of these. Build was successful, so we can test this out. Hopefully this is a little closer to 180 degrees. So I hold this down. And it did go around 180 degrees, just an additional 360 it appears. So, I mean, it basically works. It just does a little more than anticipated. So,
tune it.
Yeah, it could be tuned later. I think for now, we're going to be fine with that since it demonstrates how to, I guess, how to make a cutoff for a command, which is kind of what we were intending to show there. But, yeah, I guess that's how to make your robot do a 720. What would it be? a 540-degree turn. In case you were interested in doing that, your driver will love it, I promise. But anyway, that is it for tonight's lab session. I believe the link to the presentation is in the chat. That QR code for the WPI Lib docs should work. And if you're looking to see the answer key, or at least the code for this week's robot, an example using Spark Maxes, an example using Talon FXs, and an example using Talon SRXs should be visible in the Programming Workshop Week 2 branch. I will say none of them use deadband. I honestly didn't think I was going to need to use deadband, but then I kind of had to implement it because these controllers are a bit wonky. But that was demonstrated in the video, so hopefully you can figure that out. Those examples primarily exist to show you how to use the motor methods for each individual type of motor, since they do differ. If you guys have any questions, you can ask them. Otherwise, we are done for the night. So thank you guys for sitting through this. Hopefully you come back next Monday. We'll be going over Limelights and Git, I think. Yeah, Limelights and Git. So thanks. Bye.